Hello everyone. So in the last video, we discussed a naive way of using recursion to solve this Fibonacci problem. And we ended up with having an exponential time complexity and a linear space complexity. Uh, Now in this video, we are going to do this recursion, albeit in a clever fashion. And by that, I mean that we can think of doing instead of doing this recursion for each overlapping problem multiple times, we can see that there are instances where I'm solving the same subproblem, at multiple times. So we can avoid doing that. And a way of avoiding that is basically maintaining what is known as a memo, or let's say a register or a record that I have calculated Fibonacci of 5 once, and so therefore I don't need to do this again. And so let's say if I'm solving this this Fibonacci number for the 7th number of Fibonacci sequence, I can encounter situations where the each subtree, or let's say the each subproblem that I have encountered once is also encountered second time. And so therefore I don't need to solve this Fibonacci of 5 second time, because I already have done that. And so therefore if I maintain a record of doing that, that I've already solved for Fibonacci of 5, which is whatever that is, I don't need to do it the second time. And so therefore we are going to use a memo, which in this case is a hash map, where the hash map will maintain a key value pair. The key will be the nth value, which in this case is 5, for example, and the output of that 5, whatever the 5th number is, the answer to that will be the value. And so therefore the hash map will maintain whatever the value is at at nth level. And so what we will do is that while we are, well, if the hash table is empty, or let's say if we don't have any record of that nth number, we are going to put that number, once we calculate the Fibonacci value at that number, we are going to put that Fibonacci number in our hash table. Okay. And so if we encountered, let's say, a situation where we have already maintained, let's say, the key, let's say the 5th number of this Fibonacci sequence already exists in my memo, then I don't need to recursively call this function for n is equal to 5. I can simply get whatever the answer is at that value. And so remember that the fetching instance of from hash map is in a constant time operation. So if I want any value, I can fetch it in order of 1 time. Okay, so I will, instead of doing this recursion second time, I'll simply fetch whatever the record exists at n is equal to 5, which in this case will be the constant time operation. Okay, so instead of following this tree, what we can end up is basically let's say a somewhat reduced binary tree in some sense, where, for example, if I'm calculating Fibonacci of 9, I will do it for Fibonacci of 8, 7, 6, 5, 4, 3, 2, and 1. And then once I return from 2, I will save the record that I have the Fibonacci of 2 is this, Fibonacci of 2 is 1, and let's say Fibonacci of 1 is also 1, and therefore Fibonacci of 3 is this. While I'm calculating that, I will simply keep adding those n Fibonacci numbers at n is equal to 1 and 3 in my hash table. Okay, and so once I encountered this 2 again, I know that I already have this implementation where I already have this record of Fibonacci of 2, which is 1. And so therefore, once we come up over this child, I know that I already have a record of Fibonacci of 3, which is 1 plus 1, which is 2. Okay, and so once I come over here, I know that I have already calculated Fibonacci of 5, and therefore Likewise, whenever you encounter a node which you have already evaluated, do not evaluate it second time. And so instead of having this, big, or let's say wide tree in terms of its breadth, we can end up, having a tree which where every child, is already, is only has only a couple of children, and so therefore we don't need to evaluate each child, given that we have already encountered that child within our tree. Okay. So in this tree, where every parent has, let's say, 2 children, I know that the space complexity will be, the worst case. So let's start with time. So the time complexity will be, 2n in this case, since we have n levels. We have n depth levels, and for every level, I have 2 children. So that will be, if I have n parents and 2 children per parent, I know that, the total number of nodes in this tree is 2 of n. So the time complexity will be 2 of n, but obviously I don't need to mention this constant 2. So that, even though the strictly time complexity is strictly speaking 2 of n, I'll simply replace it with, order of n. And likewise, the space complexity, strictly speaking, will also order of 2n. And by that, I mean, imagine that, if you keep hopping and you come up until this node, what you will have is, n call stacks. The recursion will create n function stacks, which you need to save in your memory. And then, while you are reverting, you also need to maintain this memo. Okay. So your memo, in the worst case scenario, will also have n entries. Okay. So order of n for memo, and order of n for call stack, which will be order of n plus n, order of 2n. But obviously we don't need to mention this constant 2. So in this way, we'll have, a time and space complexity, a linear time and space complexity of order of n, which, comparatively speaking, in this case where, the time complexity was exponential, it's and linear. So that we had exponential time complexity and linear space complexity in this case. If we do not memorize, or if we do not maintain any record, but you see that we have we have reduced this exponential time complexity into a linear time complexity in the case of dynamic way of solving this recursion. Okay. So this was the second this is the second way of using this top-down approach. In the next video, we are going to see an iterative approach, a bottom-up approach of solving the same problem.